If you ever find yourself hiking through a mountain valley or walking along a dry riverbed, and suddenly you notice a massive boulder with a strange ribbed, quartz-filled texture running across its surface, stop. Don't walk past it. Don't assume it's just another rock, because what you're looking at could be one of the clearest geological signals of gold lurking in the ground around you. And the reason has nothing to do with luck. It has everything to do with deep Earth history, hydrothermal systems, mineral chemistry, and the way pressure fractures create the perfect gold-carrying pathways. Gold does not occur randomly. It follows structure, heat, and time. When superheated water rises from underground magmatic bodies, it carries dissolved silica, metals, and trace elements with it. As that boiling fluid forces itself upward, it infiltrates cracks, fractures, and weaknesses in hard host rock. When that fluid cools, the silica turns into quartz. The metals precipitate out, and the fracture becomes sealed. Over millions of years, the quartz hardens, the pressure changes, and the rocks shift, leaving behind a geological signature, a quartz vein. But not all quartz veins are equal. Some are barren, some look promising but lack metallic mineralization. Others, rare ones, show a texture that immediately grabs the attention of every seasoned prospector. A rib-like ladder pattern, pressure-filled quartz network that slices across a host boulder. And when you see these tight, parallel quartz infillings, especially when they run in repeated bands, it's a geological confession, a quiet truth, a signal that the same hydrothermal system responsible for forming that vein may have dropped gold nearby. This specific texture tells you something important. The boulder wasn't formed gently. It was fractured, pressurized, infused, then healed by mineral-rich fluids. The more intense the fracturing and healing, the higher the chances that metals, including gold, were left behind inside or very close to the vein system. Look closely at the quartz itself. If you see smoky tones, iron staining, rusty streaks, or tiny specks of metallic luster locked inside the quartz, that's not decoration. That's the fingerprint of mineralization. In geology, every color stands for a chemical process. Red and orange staining often signal iron oxides, the weathered remains of pyrite. And where pyrite exists, gold is often nearby. Not inside the visible iron, gold hides microscopically, dispersed in the same systems that generate sulfide minerals. Now observe the host rock. Is it granite, schist, metamorphosed volcanic rock? The type matters. Granitic terrain with high silica content is a strong environment for quartz gold veins. Schist zones tend to host structurally controlled gold deposits. And if the quartz vein cuts through dark volcanic rock, the contrast between brittle volcanic parent rock and the invading quartz often creates perfect traps for gold deposition during hydrothermal cooling. Next, check the orientation. Does the quartz vein run straight across the boulder? Does it branch? Does it form a zigzag? Straight, clean veins often indicate a single pulse of fluid. Multi-branch or zigzag patterns tell you there were multiple events, each one adding more minerals. Repeated events mean repeated chances for gold to settle. Sometimes the richest veins come from reactivated fractures that filled over and over again through geological time. The most interesting texture appears when the quartz forms a ladder vein pattern, thin parallel segments that look like rungs. These textures appear when rocks undergo repeated shearing. Each shear event splits the rock slightly, and each pulse of mineral-rich water cements it back. This is the same structural environment that forms gold-bearing veins in major mining districts across the United States, from the Mother Lode Belt of California to the gold systems of Nevada and Colorado. But here's the part most people ignore. Gold often escapes the vein itself. When pressure shifts, gold-bearing fluids may leak outward. They move into surrounding rock, spread into microfractures, and settle along the edges rather than in the center of the main quartz vein. That's why you might not see gold in the exposed quartz on the boulder. Yet gold could be just meters away in the subsurface rock. A boulder with the right quartz texture is like a billboard from nature. It tells you that the entire area once hosted a hydrothermal engine powerful enough to transport and deposit heavy metals. It also tells you that weathering, erosion, and uplift have since exposed the system. If a boulder broke off from a larger vein system uphill, the gold source is not at the boulder. It's higher up the slope, near the fracture zones where the veins originated. So follow the boulder's orientation, trace its alignment, find the direction from which it likely fell. The bedrock above may contain the original vein outcrop, sometimes called the mother vein. Even if the main vein is eroded, fragmented pieces like this boulder reveal the exact geological environment that once produced gold. Now inspect for secondary clues. Are there angular quartz fragments scattered around the area? Does the soil contain white shards? Is the ground stained with rust? Quartz float, loose quartz fragments at the surface, often lead to hidden veins. Rusty soil indicates iron oxidation, a classic companion to gold-bearing sulfide systems. Listen for the sound the quartz makes when tapped. Hard, glassy quartz with a sharp ring indicates strong crystallization. This often forms under deeper, hotter conditions more favorable for gold precipitation than shallow veins formed by low-temperature fluids. If you see vugs, small cavities inside the quartz, pay attention. Vugs are spaces where crystals grew freely. These conditions often signal a sudden pressure drop in the hydrothermal system, a moment when gold can rapidly precipitate out of solution. Sometimes gold forms in these cavities, but more commonly, the gold forms within microfractures around the vugs. Look for subtle signs of sulfides. Even if the rock has weathered for thousands of years, tiny remnants may remain. Cubic molds where pyrite used to be, brassy reflections locked deep in the quartz, or dark streaks of oxidized minerals. When pyrite oxidizes, it leaves rusty halos in the rock. Sometimes the most powerful gold traps form not during floods, but during silence. When water levels drop and the current slows, suspended particles settle gently. If you could shrink yourself and stand upon the riverbed, you would see a golden snow slowly descending through the water, grains finding resting places among gravel and black sand. This tranquil period after a flood allows the river to set its new layer of concentration, sealing it beneath the next rush of silt. Year after year, the process repeats, building hidden shelves of fine gold that only geology itself could reveal. Beneath the glimmering surface of a river, an ancient world stirs, one sculpted grain by grain, through centuries of flow and flood. Here, river gravels act as guardians of gold. They form a shifting skin of the Earth's memory, layered by time and current. Each flood rearranges these gravels, burying new gold beneath old stones. The finer the material, the deeper the secret, for gold prefers to hide where movement slows. Heavy nuggets sink through coarse gravels, then rest in compact clay below, creating hidden reservoirs that can last for millennia. While light materials wash away, gold stays, embedded in silence, guarded by pebbles and sands that never speak. When rivers slow, they whisper to clay. Clay, soft and dense, is the ultimate trap. It grips gold with molecular precision, locking it away where even floods cannot reclaim it. Over thousands of years, these clay pockets become time capsules. Layers of fine silt, organic matter, and mineralized residue compressed together, sealing flakes and dust of gold inside airtight vaults. The color may appear dull, a drab brown or gray, but underneath lies concentrated wealth, unseen by human eyes. These pockets form mostly near bends, where turbulence weakens and heavier particles settle, and each pocket becomes a secret chamber, an untouched archive of Earth's quiet chemistry. Gold rarely travels alone. It walks with iron, not by choice but by physics. Iron oxides, magnetite, and hematite act as silent partners in gold's hidden migration. When water slows, these magnetic minerals settle first, forming a shadow line that gold soon follows. Together they create a mineral signature, a natural map pointing to buried wealth. Over eons, these black sands become trails of truth. They tell of floods, shifts, and ancient channels long forgotten. But for those who observe carefully, this dark residue is not waste. It is gold's reflection in mineral form. Beneath the living rivers, dead ones lie. Ghost channels from ages past. They once flowed freely, cutting through bedrock, but were buried as the earth reshaped itself. Within these ancient beds lies the purest, oldest gold known to nature.